All right, guys. Today I'm just going to be going over a practice equilibrium problem where you could use a rice chart. So I'm going to go over in the next few videos just different types of equilibrium problems where a rice chart might help you organize your information. But I want you to understand that you don't have to when you if you're having trouble with an equilibrium problem and I go, hey, that's a rice chart problem, what I'm saying is, hey, make a rice chart. That'll help you organize your information. For all the equilibrium problems, you don't have to make a rice chart. But a lot of times, especially later on when we get to acid-base equilibrium, or later in this unit, in Unit 4, when we get to solubility product and KSP and molar solubility, a lot of times the shortcuts we come up with that we memorize because it's a shortcut, is we're coming up with those things by making a rice chart. So it's an important concept to understand, but also understand, especially in the multiple choice section of the AP exam. Sometimes it's a waste of time to make a rice chart, and if you just understand what a rice chart does, like the information you can get from a rice chart, a lot of times you can just do it in your head, and you don't have to sit there and write out the chart. But on maybe a more complicated problem, or in some instances where we're not allowed to use the shortcut, where where you'll learn about when you can use the shortcut versus what conditions you can't use the shortcut, that kind of thing. You'll get familiar with that, but understand, like if you are doing an equilibrium problem, and that doesn't have to be just equilibrium in general. It could be acid-base equilibrium. So if you're dealing with weak acids, weak bases, all that stuff, the solubility of salts at equilibrium and that kind of thing. If you have any doubt, start setting up a rice chart. And as you organize your rice chart and put in the information you know versus the information you don't know, making the rice chart, you might be able to see, oh, I have enough information in here to figure out all the information that would go into the rice chart, and now I can answer all the questions that are thrown at me. All right, so let's get into it. So if you go to the back of your equilibrium review notes, here's it has some reminders on what a rice chart is and how to set up a rice chart. So you have this to reference all the time. All right. So just make sure you kind of understand what we're doing here. So what I want us to do is I got a practice problem, and I'm just going to show you how we could set up a rice chart to answer our information about it. Okay. Whoops, wrong thing. Here we go. All right. So again, rice charts are just a way to organize your information in an equilibrium problem. Okay. What RICE stands for is reaction, initial, change, and equilibrium. So you write your reaction up here, and it's got to be balanced. You put your initial amounts here. Now, when you plug in initial amounts in a RICE chart, it's either got to be initial molarities, if you're doing a regular K, equilibrium constant, or initial partial pressures, if you're doing a KP, okay? But not moles, not grams. So if you're given moles, you got to divide by the volume to make it molarity. Or let's say you're given moles and you needed partial pressure, you got to plug it into Pivnerd and solve for the partial pressure. That's pretty rare. I haven't seen that before on an AP exam, but that's what you would do. If you're given grams, you'd have to convert to moles and then divide by the volume to get molarity. So just understand that any amounts, any numbers that you're putting into a rice chart in the initial category, the equilibrium, has to be either molarity, moles per liter, or partial pressures. So if you're given moles, but the container is 1 liter, then moles is molarity. But be careful. I've seen some questions on the AP exam where they give you moles of everything initially, and then you're making a rice chart, but the volume's in 2 liters, not 1 liter, and so you got to make sure you take your moles and divide by 2 liters, and you should be plugging in molarities into here. All right. So just things to look out for. Okay. And so let's give it a problem. All right. So in this problem, we're using a rice chart to find the equilibrium concentrations, And if we know the equilibrium concentrations, then we can actually calculate the equilibrium constant. Okay, so let me show you what I mean by that. All right. So in this scenario, we're given the initial amounts and one of our final amounts. And by final amount, I mean one of our equilibrium amounts. Okay. So let's look at the problem. All right, so we're told that 2.5 moles per liter of hydrogen reacts with 1.0 moles per liter of nitrogen to form ammonia. It is found that at equilibrium, the molarity of H2 is 1.75. So if we notice, we started with 2.5 molar H2 and it went down to 1.75 molar, okay? So notice we're given the initial amounts, 2.5, 1.0 for nitrogen, and 0 for ammonia. And we're given one of our final amounts, the equilibrium amount of H2. And from that, we're actually supposed to calculate the equilibrium constant K at this temperature, okay? So let's kind of understand what we're trying to do, right? So here's our reaction. We got 3 hydrogens plus a nitrogen yield 2 ammonias, okay? The equilibrium constant is equal to the equilibrium expression of the reaction, and we get the equilibrium expression by doing products over reactants, coefficients become exponents, don't use solids, don't use liquids. So these are all gases, so we're going to use everything. So we would do the concentration of ammonia squared over the concentration of hydrogen cubed over the concentration of nitrogen. And notice I threw in this little EQ here. That's a reminder. I can't plug in initial amounts. It's got to be equilibrium amounts to get the equilibrium constant. So don't, jump the gun and go back to this problem and plug 2.5 in for the molarity of hydrogen. That was the initial molarity of hydrogen, but not the equilibrium. The equilibrium concentration for hydrogen was 1.75. So if this is my equilibrium constant expression, I know that what I'm going to plug in here is 1.75 for the hydrogen because that's the equilibrium concentration of hydrogen. So I know that one, but in order to calculate K, I got to figure out this one and that one as well. So, we might be able to do this in our head, but let me show you how a rice chart helps us organize our information, all right? So we're going to make a rice chart with the information that was given to us here, all right? So the way we set it up is we write our reaction, okay? And then for our initial, we're going to put our initial molarity. So initially, in our container, we had 2.5 moles per liter of H2. We had 1 mole per liter of nitrogen. And before the reaction starts, we have 0 of the product. So we have 0 NH3. Okay? Now, here's something to understand to figure out the change. Okay? The change in the molarity, the change in the concentration as we go from initial to equilibrium conditions. Okay? So, as this reaction proceeds, we know we need to get some ammonia to be at equilibrium, right? You can't have 0 of anything at equilibrium. So we know the reaction is going to have to shift this way to reach equilibrium. So as the reaction shifts towards the right and produces product, we're going to lose the things on this side of the equation, and we're going to gain things on this side of the equation. So it's going to be minus X on the reactant side, and it's going to be plus X on the product side. So my change on my reactant is going to be minus. My change of my product side is going to be plus, okay? Because I know in order to reach equilibrium, I have to get some of this. And the only way that can happen is if I lose some of this, all right? Now, this is where we got to watch out for the stoichiometric ratios, right? The amount of hydrogen I'm going to lose is not equal to the amount of nitrogen I'm going to lose because you lose 3 hydrogens for every 1 nitrogen, okay? So instead of just saying minus X, it's minus 3X, okay, for the hydrogen. So whatever the coefficient is, you're going to include that in the change. So minus 3X for the hydrogen, minus X, 1X, for the nitrogen because its coefficient's 1. And then again, think about it. For every 1 of these I lose, I gain 2 of these. For every 3 of these that I lose, I gain 2 of these. So we're going to say plus 2x for the ammonia. Okay, so that's going to be my change. And now all you have to do is initial plus the change. So the equilibrium concentrations for everything is for hydrogen is going to be 2.5 minus 3x. So the equilibrium molarity of hydrogen is going to be 2.5 minus 3x. The equilibrium concentration for nitrogen is going to be 1 minus x. And the equilibrium concentration of ammonia is going to be 0 plus 2x, so just 2x. All right? And so now all I need, remember our goal is we need to plug the equilibrium molarities into this expression so we can get a value for K. All I need to do is figure out what x is equal to, and if I know what x is equal to, I can figure out what that number is, figure out what that number is, figure out what that number is, and those are my equilibrium molarities, and that is what I would plug in to my equilibrium expression to solve for K. All right? So remember, in the problem, we were actually given the equilibrium molarity. So yeah, the equilibrium molarity of this one was given to us, not this one. So now we know what that equilibrium molarity is equal to. We can say 2.5 minus 3x equals the equilibrium molarity of hydrogen. And remember, it was 1.75. All right? So if we look at our Rice chart, kind of reorganized, right, we can have these equilibrium concentrations in terms of x, but we don't need that for the hydrogen because they told us what it was. And now we can use this part. If we have the initial amount and we have the final amount and we know what the change is, we can solve for x. And once we solve for x, that unlocks everything in the box here. It unlocks everything in the chart. And now we can get that number, and we can plug those in to our equilibrium expression. Okay, so we'll use this to solve for x. So we'll say 2.5 minus 3x equals 1.75. X is 0.25. And now I just plug in 0.25 in for here, and I plug in 0.25 in for here. And so now we have our equilibrium molarities. The units of this would be moles per liter. So at equilibrium, the hydrogen's 1.75, the nitrogen's 0.75 moles per liter, and the ammonia is 0.5. Now all we have to do is take those numbers, plug them into the equilibrium expression. So let's recall our equilibrium expression. Don't forget to square the ammonia. Don't forget to cube the hydrogen. So the ammonia was 0.5 at equilibrium. So 0.5 squared divided by 1.75 cubed, and then divided by 0.75. And that'll give us our answer. So we plug in those numbers, we get our value of K. A lot of times K is put in scientific notation. You don't need to do that. But what does this mean? It means K is less than 1. And what does that mean? That means the forward reaction for that process of producing ammonia is not favored at whatever temperature this reaction was set up at. So the reaction is not thermodynamically favored at this temperature because K is less than 1. All right? So again, there's a lot of different, things that we can use Rice charts for. Okay, it's not just going to be this scenario, yet this tends to be one of the scenarios. Like a lot of times you might see a question like this, instead of them asking, so basically given the same stuff, but instead of asking to actually get the equilibrium constant, they'll just say, well, what's the equilibrium concentration of ammonia? All right, and then so we could set up a Rice chart and solve for x, and then say, okay, well, the equilibrium concentration of ammonia is 0.5, okay? So again, anything in this chart that we figured out could be asked about in a question like this, but, we're just kind of putting everything together to solve for the equilibrium constant at the end here. Okay, so again, I'm going to show you, so we're going to have some other videos going over some other similar problems, but just maybe asked differently, maybe given different things. But in the end, setting up a Rice chart kind of helps us organize the information and then figure out, okay, well, this is what I need. And then this is what I have in my Rice chart. I can unlock the Rice chart by solving for X. And then once I have all those values, now I could figure out K, or I could write the equilibrium expression or whatever. Or the hard one is going to be, not the hard one, but the other scenario that's most common is they give you only initial conditions. They don't give you any of the final molarities, but they give you the value of K. So you take your equilibrium concentrations in terms of X at the race chart level. So let me go back and show you. So you make a race chart like this, where you get your equilibrium concentrations in terms of X, and then you plug those into the equilibrium expression. And if you were given the K value, you could plug the K value in here, and then you could solve for X to end up getting all your equilibrium concentrations. We didn't have to do that here, A, because we weren't given the equilibrium constant. And if you know one of your equilibrium molarities, then you can figure out all of them without having to do some advanced algebra stuff, all right? But we'll worry about that later. I'll show you some examples with that later. But I just wanted to kind of show you, kind of give you an idea of what's to come. You know, we'll have a couple more videos going over some different types of race chart problems you might see. But again, a lot of times it could be a problem that you can set up a race chart for that'll help you out. But a lot of times that can be a waste of time because it could be something that you do in your head. So if you understand what we were doing in the race chart, a lot of times you can do that math without making the chart and wasting time, you know, writing it down. You could do it in your head and go, okay, well, I'm going to lose 3 times, like, so I'm going to, if I lose this much hydrogen times 2/3 is how much, you know, ammonia I'm going to gain, that kind of thing. So it's just stoichiometry in the end. So, yeah. All right. So I hope that helps.